7.4 Energy and Efficiency from page 145 to 149 of your Science Connect 1 textbook. When any simple machine is used, energy is lost due to friction, heat, or incomplete combustion. Friction is generated between two moving parts. So, for instance, sliding something up a ramp, where those two are in connection, you will experience a bit of a heat generated. Or in the mechanisms of pulleys, wheels and axles, etc. Heat can be given off by a cooling system or exhaust. So within our cars, for instance, we are always losing energy via heat and exhaust. Poor or incomplete combustion, if fuel is included or required. So for instance, for machinery, incomplete combustion means that energy can be given off as smoke or soot instead of being turned into heat or any sort of work. The amount of work or energy put in is always greater than the amount of useful work or energy put out. Input is greater than output. Efficiency is this comparison of the output to the input. Nothing is 100% efficient. There's always an energy loss. Okay, so our efficiency will always be less than 100. Efficiency, if you're curious, is calculated by the output energy, because that's the smaller number, divided by the input energy, because that's the larger number. And when we want to turn something into a percent, we multiply by 100%. So some examples of efficiency. If we're using a pulley to pull an object up, there will be energy lost due to friction between the rope and the pulley itself here. And there could be energy lost due to friction because this has to spin on an axle here. So loss of friction with pulley and the wheel itself. So our energy input will always be greater than the energy output. Efficient appliances around your house and different practices like turning off lights, putting on a sweater instead of turning the heat up, help to conserve energy and money. This helps both our budget and the environment. I included this little graphic because I thought it was kind of interesting. It may be a little bit outdated. But how much electricity, so energy, do appliances in our home use? You can see that a water heater, in this case, is the largest consumer of energy in our home. So hot water on demand costs us the most per year. A dryer is next up. I don't know if anybody in Calgary or Airdrie has a pool, but a pool or a hot tub pump and heater is actually probably more than a water heater itself. A fridge or a freezer is the largest in our kitchen appliances. Computers that you leave on, you kind of leave it on in the background, it falls asleep. TVs, microwaves, dishwashers, clothes washers, etc. So some of our kitchen appliances have a small electricity usage because we don't use them constantly. I don't make toast all day long. If I did, it may be up a little bit higher. Same with our dishwasher. It's something we run periodically. So why is a clothes dryer higher in energy? Well, probably because of the heat requirement. Heating up that element takes a lot of energy. So light bulbs have been changing over time. We started lights with incandescent bulbs. Those are like the original, the OGs. Then we went to a CFL. And most lately, we are looking at LED bulbs. So which would you choose for your home and why? Well, you can see that the yearly operating cost for every light bulb, a 60-watt bulb, is about $13. As a CFL, the operating cost goes down to $3. The LED is just a little bit less at $250, $260. The energy usage of an incandescent bulb is quite high. It's got 60 watts. Energy usage for a CFL is just a little bit, quite a bit less, at 14 watts. And for an LED, just a little bit less at 12 watts. They all use or give off the same amount of light. That's what this is saying. Even though they have different wattages, they give off the exact same brightness. The lifetime of an incandescent bulb is 750 hours. So that's when you'd have to change it. A CFL is 10,000 hours, so greater than 10 times the amount of our incandescent. A LED is 5 times as long or more. So which would you choose for your home? I'd probably want to choose an LED bulb. Why? Simply because I don't have to change it very often, gives me the same brightness, uses less energy, and costs me less per year in its usage. Why have we moved away from incandescent light bulbs? Well, their cost per year is quite expensive. They use a lot of energy, and I have to change them frequently. Additionally, they're just not efficient. Incandescent bulbs are the type that heat up when they are being used. So to change an incandescent bulb, you wouldn't want to touch it after it's been used. It gets very warm. So is that efficient? Probably not. Whereas an LED bulb stays cool the whole time. It does not heat up. We have no energy loss due to heat like we do in an incandescent. Maybe a little bit, but not very noticeable. Where do incandescent bulbs still have a place in society? The fact that they give off heat is actually kind of helpful. Oftentimes, they're put in chicken coops or other little farm animal enclosures to give off heat as a heat lamp. They will change them from a bright light to typically a red light for a heat bulb. The only drawback for an LED is the initial cost. The cost of an LED bulb is quite a bit larger than an incandescent bulb or a CFL bulb itself. So the upfront cost of changing these LEDs in our home is a lot larger, but the cost savings in the long run should be worth it. You may have seen some of these Enter Guide stickers if you've ever looked at an appliance in your home. There are 4 things that are displayed on the label and 2 that are really important to us here. The annual energy consumption of the model, so whatever appliance it is, in kilowatt hours. And it includes an energy consumption indicator, which positions the model. Let's say we're looking at a dryer, the particular model of dryer that you have, with the most efficient dryer and the least efficient dryer on the market. Okay, so I'm not even sure what this is that we're looking at here, but the most efficient model on the market has a usage of 481 kilowatt hours. The least efficient has 683 kilowatt hours. So our model is closer to the low end. For those of you unfamiliar, a kilowatt hour means how much electricity it would take to run that appliance for 1 hour. A few other things on the label: the type and capacity of models that make up this class, and the model number of what's actually being compared. So these are things that I wouldn't be looking at as closely, but if I was trying to make a comparison between 2 different models, I'd want to make sure that they were falling within the same class. Okay. This is a required sticker and representation on all washers, dryers, dishwashers, freezer, ovens, fridges, and portable air conditioners in Canada. We don't actually have to put them on any other heating device. So we don't need them on furnaces or hot water tanks or like the whole house if you had air conditioner. So when considering buying a new appliance, where would you want the indicator to fall on the scale? Again, you would probably want to use less energy to run that appliance for 1 hour than more energy because it's more efficient and it'll cost you less. Most energy in Canada comes from burning fossil fuels. I have a little energy chart here. This is from 2014, but it's still fairly accurate. Not a whole lot has changed. The strong majority of our electricity in Alberta is generated by burning coal. This turns turbines, which generate electricity. So about half of our energy, our electrical energy, is made by coal. The other is by gas, so typically like a natural gas. About 4% of our energy in Alberta comes from wind farms. There's a wind farm in Pincher Creek and a few others around Alberta. Biomass, so a biofuel. Hydro, so that would be rivers. In BC, hydroelectric is much larger percentage. And other types of electricity generation like solar. The fact that we burn fossil fuels, which includes gas and coal, for most of our electricity leads to environmental concerns. This is because these produce our greenhouse gases, which are contributing to global warming. They're also a non-renewable energy source, so we are using them up. We need to look at potentially expanding some of our alternative fuels to start slowly making up some of the percentages here so that we can slowly transfer towards a greener and more sustainable electricity generation. Given that our table has not changed much from 2014 to current, it's an indicator that we are not moving forward with too many of our renewable source energy developments. How can we help? Well, beyond looking at putting up solar panels on your house and maybe a wind turbine in your backyard. There's a few other ways we can do this. And the biggest one is to reduce the amount of energy that you use. So use less, unplug things that you're not using. Try and use more efficient appliances if that's something you can do. And choose alternatives like bike to work or school. If you can afford a hybrid or an electric car, that could be better as well than using our general diesel or gas cars. Again, we could look at solar panels or a wind turbine if we lived in a very windy area, and that would be economically viable. They're kind of expensive to install, so we have to make sure that we're looking at the return on our value. In some areas, geothermal heat is something available to houses. What happens is cold water is pumped down deep into the ground where we are getting closer to the Earth's crust and core, and this heats up the water and brings it back into the home. That heat is then used to heat the house itself and can be used to heat water for just running hot water or having a shower. So that's really great in the winter, but in the summer, hot water can also be pumped down and turned into cooler water. This is because our ground in the summer is cooler than in the air temperature outside. So geothermal heating is something that was kind of being developed and used a little bit more frequently on Vancouver Island. I don't know, about 5 or 10 years ago, it started to really pop up there. So it may not be as viable in Alberta, but in locations where it is viable, or Calgary, sorry, in locations where it is viable, we should maybe look at those as an alternative and consider them before using our traditional energy and efficiency models. There's some practice on page 149 of your Science Connect 1 textbook, numbers 1, 2, 3, and 4.